Imagine gazing out into the cosmic abyss, not just at static star fields, but at a universe in constant, dramatic motion. For nearly a century, we've known our universe is expanding, carrying galaxies away from each other like raisins in a rising loaf of bread. This was Edwin Hubble's monumental revelation in the 1920s, forever changing our understanding of existence. For decades, the prevailing wisdom, rooted in the very fabric of gravity, dictated that this expansion should be slowing down. The universe, massive and interconnected, was expected to decelerate under its own gravitational pull, perhaps even eventually reversing into a big crunch. It was a coherent, elegant picture until a series of observations in the late 1990s utterly shattered it. Suddenly, we faced a revelation so profound, so counterintuitive, it forced us to invent an entirely new component of reality. The universe isn't just expanding, it's expanding faster and faster. Something is actively pushing it apart. This is the story of dark energy, the enigmatic force that dominates our cosmos, dictating its past, present, and unimaginable future. Before the 20th century, the cosmos was largely perceived as static, unchanging, an eternal backdrop to our existence. Albert Einstein himself initially introduced a cosmological constant into his equations of general relativity precisely to maintain a static universe, a decision he later called his biggest blunder. But in the 1920s, a determined astronomer named Edwin Hubble, using the then colossal 100-inch Hooker telescope at Mount Wilson, began to unravel a different truth. By meticulously observing distant nebulae, which he proved were in fact other galaxies, Hubble noticed a peculiar phenomenon. The light from these galaxies was consistently red-shifted. This redshift, explained by the Doppler effect, meant these galaxies were moving away from us. Furthermore, the farther a galaxy was, the faster it appeared to recede. This direct proportionality between distance and recession velocity became known as Hubble's law. It was the irrefutable evidence that the universe was not static. It was in a grand, continuous state of expansion. This discovery birthed modern cosmology, replacing the static model with a dynamic, evolving cosmos, setting the stage for the Big Bang theory, and leading to the expectation that this expansion would inevitably slow down. With Hubble's groundbreaking work establishing an expanding universe, the next logical step for cosmologists was to determine the rate of this expansion's change. Gravity, being an attractive force, should inherently be slowing the universe down. The question was, by how much? Would it slow enough to eventually reverse, leading to a big crunch? Or would it forever expand, albeit at an ever-decreasing rate? To answer this, scientists needed a reliable standard candle, an object with a known intrinsic brightness that could be observed across vast cosmic distances. Enter Type Ia supernovae. These colossal stellar explosions occur when a white dwarf star in a binary system accretes enough material from its companion to exceed the Chandrasekhar limit of 1.4 solar masses. This triggers a runaway thermonuclear fusion reaction, resulting in a cataclysmic blast that consistently reaches a peak luminosity. Because of this uniformity, Type Ia supernovae serve as exquisitely precise cosmic yardsticks, allowing astronomers to measure distances to galaxies billions of light-years away, and, crucially, to track the universe's expansion history. The race was on, with two independent research teams, the High Z Supernova Search Team and the Supernova Cosmology Project, vying to pinpoint the universe's deceleration.